In this section, we're going to discuss the concept of finding a remainder or an error. And so if we look at the idea of a remainder, we know that that is some portion that is kind of left over, so to speak. So if we have a series, and we know the series is continuous and decreasing, we know, in fact, we're not even going to allow it to stay the same. So it's really not even non-increasing, but it's strictly decreasing. So we know we have some sort of general shape that looks like this. And the series, then, we know that we can approximate the series by looking at, basically, we can say that this is basically a Riemann sum. And so the idea then is, how do we, if we know the sum of the series, how can we get this idea of calculating a remainder if we only go out so many terms? So if we just take a look at this, and this is where the integral test helps us, since integral is talking about a summation process, much like this is a summation process. So if we look at then this series, and we model this series as a function, then we can take a look at that integral test. And so if we know then, performing the integral test is literally finding the area under this curve. And if we approximate sums of series, then that is a lot like saying, well, I'm going to look at this right Riemann sum. And so if I look at this right Riemann sum, then I can kind of get a Riemann sum looking picture here as I approach some value n. So if we look at this Riemann sum is really kind of what we think of as the sum of the series. So in this situation, we have a right sum here because of the right corner of the box coming up to that function. And so each one of these boxes then is, if this is A1, then the height of this is f of A1 times 1. And so we can accumulate this area here. And so this Riemann sum then is literally the partial sum of the series. And so then if we look at the area from an integration standpoint, if we look at the area up to that point, we know that the value of the area is a little bit larger than the Riemann sum. And so then that leaves then, if we know then that if we don't know the sum of the series, so if we don't know, this would be the sum of the infinite series. And if that's unknown, then we really can get an idea of a remainder here or an error by considering that we can take this as a function and find the area underneath the curve. So we can go ahead and find the area here all the way out to infinity. And so if we do that, if we represent that as the area from the area really of f of x all the way out to infinity dx, then we know that this area, and let me just kind of make this a little bit transparent so we can start to see. Not just that area, but the box is a little better. So we know that that total area then we can find using the integral. And so if this is the partial sum that we have here, then this area here beyond that partial sum is the leftover part. And so this leftover part here leftover part, or this leftover area, becomes then what we call the remainder. And another term they might use is error. It's really the difference between the infinite sum and this partial sum here that we can find by adding up a finite number of terms. And so from a just a conceptual standpoint, this area, this remainder here, then we can say, well, it's really this portion of the function integrated. So this this remainder, so to speak, is equal to from where we start, which is at the nth term, all the way out to infinity. This remainder is that much. At most, we also have to kind of keep in mind that the actual sum of the series is an underestimate, is an estimate that we find by doing a Riemann sum. And so that being the case, then the actual, if we would continue to add up the rectangles in this area, these rectangles would represent the remainder. This integral is somewhat larger than that. So what we say then is the remainder of the infinite series has got to be less than, or at most equal to, that value. And so that represents the remainder then. And if we come back up here, then they just kind of also bound the remainder by 0 and that value. And so looking at this, then they define the remainder as the actual sum minus the partial sum. So if we knew this partial sum, if that was some finite value that we knew, and we knew the actual sum, we could find the actual remainder. So while the remainder of this series will be at most the value of that integral, the actual remainder would be the value of the infinite series minus the value of the partial sum. And so we can really calculate two things. This is the thing that we're really more concerned about, is just maximizing the remainder, or maximizing the error of a series. Questions involving the remainder of a series fall into 3 categories. The first category is approximating a partial sum. So in other words, literally adding together a certain number of terms. The second category is to estimate the maximum error. In other words, find R sub n, find the maximum value of R sub n. And then the third category that these fall into is find how many terms you have to go out to so how many terms needed in order to get a remainder that's less than a certain value. So in other words, we want to find how much of the series we need to take in order to get a value that we can use for the sum that we know isn't the exact sum of the infinite series, but is at least this close to the actual sum. And so those are the three major categories of problems that they would possibly ask you, the College Board would ask you. So let's start out with this part, the idea of a partial sum here. We want to approximate the fourth partial sum. In other words, we want to find S4. And if we want to find S4, that means we have to add together. In other words, we are looking at not an infinite series, but in a series that starts at 1 and ends at 4 of 1 over n to the 3 halves. And so that is literally taking these rectangles. So these first 4 rectangles. So here's the first rectangle, here's the second rectangle, here's the third rectangle, and here's the fourth rectangle. So, you know, this is literally just like a Riemann sum, a right Riemann sum. So this is going to be our, altogether that's going to be our S4. So we're going to go ahead and substitute 1 in here. 1 to the 3 halves is 1, 1 over 1 is 1. Then go ahead and 2 to the 3 halves in the denominator, so that's 1 over 2 to the 3 halves, and then 1 over 3 to the 3 halves, and 1 over 4 to the 3 halves. Okay, so we're looking at this as 1 plus, let's see, 2 cubed is 8, so that's 1 over the square root of 8. And plus 3 to the third is 3 times 3 is 9, times 3 is 27, 1 over the square root of 27, plus, and then this one is 4 cubed is 64, take the square root of 64 is 1 over 8. And so if we add those up, we end up getting about 1.671. At this point, it's clear that we're not going to be able to find a common denominator. Decimal approximations are perfectly appropriate in this situation. And according to the College Board, we round to 3 decimal places. Okay, so that would be an appropriate answer when you take the AP exam. If we take a look at this just from a talking about convergence or divergence, we're told that it's a convergent series. We know it's a P series, it's of that form. We can test for convergence if we look at the p-value. We have a p-value of 3 halves. And we know that since we have a p-value of 3 halves, which is definitely greater than 1, that we do have convergence. If we look at the next type of problem, estimate the maximum error, we know that that maximum error is going to be no bigger than the area underneath the function from n out to infinity. At most, it's going to be that much. You know, if we would draw green rectangles in here, all of those rectangles would be littler. They would lie beneath this function. So we know the rectangles themselves would add up to something less, but we don't care that it's something less because we are being asked to find a maximum error. And so the maximum error is defined as, remember this is what the statement is saying here, the error is going to be less than or equal to this. In other words, this value is going to be as big as it gets. So from n to infinity, f of x dx. So for this particular problem, if we were to look at the fourth partial sum, which is 1.671, the maximum error would be then to sum up, really, to sum up all the way back to here. So this is your R4. So this is your error for a partial sum of 4. And we're going to then start summing up the green rectangles from 4 to infinity. Okay, so we know this is 1, 2, 3, 4. So that's why we're integrating from 4 to infinity. We're leaving the first 4 rectangles as part of the sum and the remainder of the stuff as part of the remainder. So that would be 1 over x to the 3 halves dx. So looking at that, that's integrating from 4 to infinity of x to the minus 3 halves power dx. So bumping up the power by 1 would be a negative half. Reciprocal of negative a half is negative 2. X to the negative half, evaluated from 4 to infinity. And really this is really improper here. And I'm kind of glossing over the fact that this is improper, like section 8 of the last chapter. So really what we're looking at is the limit as b goes to infinity of, and I don't really need to write the integral sign, limit as b goes to infinity of minus 2 divided by the square root of x from 4 to infinity. So we're talking about the limit as, this is b. So the limit as b goes to infinity of minus 2 over the square root of b cubed. Not cubed. The square root of b minus a negative 2 over the square root of 4. And so as we look at that, we know that we can put infinity here. We get 0. Minus a negative is a positive, and so we end up getting a positive 1. So the remainder then for the fourth partial sum is 1 at most. So if the remainder is at most 1, that's the biggest remainder or error there is, then if we look back at this fourth partial sum, for a remainder of 1, okay, so for a remainder equal to at most 1, if our fourth partial sum is 1.671, then our infinite sum at most, just to kind of give you an idea here, at most the infinite sum of the series, in other words, the sum of the series from 1 to infinity at most could be 2.671. If we're off by 1, this is how far we are off from the actual error at most. So the sum could be at most this much. What the actual sum is, I am not altogether sure. So if we look at this, then the next type of question is, how far do we have to go out? So what does this stopping point need to be in order to have a remainder of less than 1/1000th? So that's what that is. So in other words, a remainder of 1 is way too big. That's too much to be off by. But if we can be only off by 0.001, so instead of this being, if this is our partial sum of 1.671, but we could actually be 2.671, that's really far off. But if this is our sum of 1.671 and we're only off by 1,000th, then we're talking about only changing this decimal place. So the question is, we have to go out much farther than 4 to get to that scenario. So what we're talking about then is, we know that we want a remainder at most. So it has to be less than or equal to 1/1000th. And we know that the expression for the remainder is to integrate the function from n out to infinity. And so what we're looking for then, if we kind of draw this picture here, so here's our function. Here's, just for lack of a reference, or just for a reference point here, here's 4, but we need to come way out here. We need to come way out here to some value n in order to get this to be at most 1/1000th. Okay, so we need to integrate from n to infinity to see where we have to be in order to get this area to match up to 1/1000th. So 1 over x to the 3 halves dx. And so when we integrate this, and I integrated it before, we know we get minus 2 over the square root of x. And we're talking about looking at the limit of that from b to infinity. So I'm just kind of picking up the integration process from this point right here. Okay, here's our integration process. And so we're talking about, and we'll end up comparing it to 1/1000th in a second here. I'm just going to kind of write a couple of steps here. So the limit as b goes to infinity of minus 2 over the square root of b minus a negative 2 over the square root of n. So that's kind of what we have to solve for. And so evaluating this, we know this goes to 0, and that takes care of this. Since b is not part of this expression, we don't really need the limit as b goes to infinity anymore. So what we're left with is 2 over the square root of n, oops, wrong type of n, 2 over the square root of capital N, which denotes that location. When is this less than 1/1000th? Okay, so we want to know when this value is less than or equal to 1/1000th. There we go. Forgot the inequality there. And so, and I messed up on that inequality as well. It should be, this is less than, so this is bigger than 1/1000th. So 1/1000th is bigger than the remainder. And so that's really kind of confusing. So I think I actually might doctor that up just a little bit more. So what we're saying is when this expression is less than or equal to 1/1000th. I think it's probably easier to see. So that being the case, really, what values do I have to stick in for n in order to get that to be the case? And we can do one of two things. We can either make a table at this point, like if n equals 1, then 2 over root n is equal to 2. If n equals 2, then this is 2 over root 2, etc., etc. And we can keep going down until this gets to be 1/1000th, or we can just solve this algebraically by cross multiplying. So we can say 2 times 1,000 is 2,000, and that's got to be less than or equal to n square root of n times 1, which is the square root of n. Then we can square both sides. And if we square both sides, then we get n has to go out to 2,000 squared, which is 4. Which is 4 million terms. So we would have to add together 4 million terms to get an error of less than 1/1000th.